Welcome, I'm Bill Wake. This is my weekly summary of the programming work we've been doing on Twitch this week. And lately we've been working on a compiler and interpreter for a language called 10th that's an imitator of 4th. We're using ARM64 assembly language, and we're working with test-driven development. So this last week we did the last bit of our compiler was compile time string constants. And we also started researching how to do input. We want to do character to time input like raw mode in Unix. And so we did some exploration of that to try and figure out what do we need to do to set that up. To do that, we needed a couple of routines, set bits at and clear bits at, and we need to enter and exit raw mode. And then finally we could implement getc that returns a character in raw mode. And we also wanted to do a random number generator, so we did a small version of that, or a pretty primitive one that'll be enough for the simple cases I expect we'll have. All right, so compiling, normally we create something that talks or puts items in this, what we call a secondary area, secondary space. We have primaries, which are assembly language routines, and then secondaries are lists of routines to call, and that's effectively what we compile to. So for pushing a string, well, pushing a number is just push followed by a number, and the number goes on the stack. Pushing a string, we're going to push the addresses. So the push command first there is going to need a pointer to the string. Well, that is going to be in the secondary itself, so we just point forward a few words and we'll get it there. Then we're going to jump around the string and, just so you skip past it, just so we have somewhere to put it in our program text in effect. All right, and then you have the actual bytes of the string, followed by some padding bytes. The structure needs to align on 8-byte boundaries, 64 bits. And so if a string is not exactly 64, doesn't end in a multiple of 8, I guess you'd say, it needs some padding so it aligns everything else. And then at the bottom there, around string, well, whatever's next, whatever gets compiled next there will always be at least something, an end routine, if nothing else. The jump points to that piece, and it's left ready to go for the next thing that gets compiled in. All right, and then here's the implementation, and it's actually pretty close to what that picture is. 174, we get the address of the push routine, and store sec is a macro that writes that to the secondary area. It manages the secondary space register, and we'll use that in the next line. 178, we're going to add 24, so we're moving. The pointer says skip over me and skip over the jump instruction, the 2-word jump instruction, and that's where the string will be. And then we put in the address of the jump, and then we're going to put in, we put in a -1. You can see it in 187. But before we put that in, we capture the current secondary space pointer. And so we'll patch that later because we don't know how big the string is going to be yet. So pushing that on the control stack lets us go back and back patch that. Then we finally store the string. It's got a method define string that knows how to write strings to secondary space and does the padding bytes I mentioned. And then final one there, we pop that address off the stack, and that's where we want to patch. We want to put the current secondary space register in there. So that's in effect making the jump point to whatever secondary space is going to write next, whatever gets compiled after the string in the source code. All right, and so next we're going on to the stuff required for a getc command, a get character. And one of those is we need to clear bits and set bits. And here I've just got a test for clear bits at, just to demonstrate kind of this, how TDD looks in assembly language. Look on the right, you'll see L-clear bits has 2 words, 107 and OX2 something. And then clear bits expected is another quad constant, and that one has the bits we're testing already cleared out. So the test case is going to use this. So first step, we're going to load the X0 register is going to point to clear bits. X1 is then the offset to the second word. It's 0 base, so the offset is 1. And then 108 is the bits to flip, which I think is bits 16 and 3. Okay, so that's the setup. Then we call clear bits at, and then we assert we're going to check that the value in line 28 is now the same as the value in line 31. So we got to get X0 holding that first value. So we load clear bits into the register, the address of it, add 8. So we move to the second word. LDR loads the contents, that 2000, well, it was 5 CV. We're going to check if it's what we expect now. That's X0. Then X1, we load the address for clear bits expected and load its contents. And then assert equal checks that X0 equals X1. If not, it prints an error. If so, it passes the test. And then we're done. Okay, this test works now because clear bits works. The constants I chose ones that were going to be used in writing the terminal attributes. I could have chosen totally different ones, but that was handy enough to make sure those particular ones worked. All right, and here's the code. We'll look at set bits at first. X0 points to the word array. X1 points to that offset. X2 is the bits to set. And really, you just load that value. The stuff in brackets, X0, X1, LSL3, is equivalent to saying X0 plus X1 times 8. Okay, logical shift left 3 is effectively a multiply by 8. So that gets us from a word address to a byte address that we need. And we load the contents there, call OR on it. So any bits that are 1 will be set after the OR, and the other bits are left as they are. And then we store that value in the same address. So we're there with our corrected, with our bit set. Clear bits at is similar. The first line LDR X3, same logic, X0 plus X1 times 8. We don't have a direct clear command that I know of in assembly language on ARM64. So we do a logical not. We take our bit that was a 1, turn it into a 0, turn all the zeros into 1s. So we can do an AND, because AND and OR are complements for this. If any bit is cleared in our knotted negated word, then it gets cleared in the and if it's set and then the word, it gets left alone, basically. So we do that computation, store the result in the same address we got it from, and return. So this gets our bits cleared as we want. All right, so now this is the part that needed all the research. We needed a function to get the terminal attributes. So I made a macro out of it. It takes a file descriptor and a term iOS struct, which is the structure that the IOCTL driver, the terminal driver, will use to write these attributes in. And to get that, X0 gets the file descriptor, which is usually 0 for standard in. And then we need this magic number. We don't have a way to load long constants in one go. So you do this two-part load. You load the lower bits and then load the upper bits by shifting it left 16 bits first. And so you get 40487413, and that has specific meaning to the IO command, the IO control command. So 40, I'm not sure what that part means, but it's an @ sign. I don't know if it's a marker or what. But anyway, that's the number that gets used, so we kept that number. Then 48 is the size of the structure we're going to write. So it's 72 base 10, it's 9 words. And then a 74 is a lowercase t, and that tells IO control, hey, we're going to talk about the terminal. You could also be talking about a printer or something else, I guess. And then 19 decimal is the code for get attributes. So the T19 part is the part that really says, hey, this is get attributes. And so that constant ends up in X1, W1. X2 then gets the pointer to the structure. So it's like passing by reference. That's the memory that's going to get filled in. Then we call Unix IOCTL. That's another macro. I didn't show it, but basically it calls a Unix service. It sets a couple address registers and calls the service. And the end result is the memory that you set aside, term iOS struct, now has the contents of those words that the terminal, the IOCTL command filled in for you. Set terminal attributes is more or less the same. It's just a different crazy constant in the middle. Okay, and then to enter and exit raw mode, that's sort of the missing piece for us. We enter raw mode, we're going to get 2 copies of the attributes, ltermios original and ltermios altered. We're going to keep the original as it was, and we're going to alter the altered one. So to alter it, we're going to clear echo and canonical flags. So normally echo is on, which says if they type a character, print the character. And iCanonical is on, which says if they're entering it, wait till you have a whole line, support the delete key, maybe support arrows, support Control A, whatever keystrokes are there. Well, we're turning all that off. We're just saying we want to get one character at a time. So we've cleared those two we've set those two flags, and now we call clear bits at on them. The space in the terminal structure, at the right word, is going to have those flags cleared. And then we call set terminal attributes, and that takes the word we altered and loads it into the driver. So it effectively puts it into raw mode. Then to exit raw mode, well, we're going to take advantage of the fact that we kept two copies around. So we have LTerm iOS original with the original attributes. We're just going to put those back. To do getc, you first enter raw mode, then you do a one character read. That's 235. You've set up some registers and do that. And you take the value that results from the read, you load the address of the buffer, you get the constant that got read, and then you push that on our data stack. And then finally we exit raw mode. All right. And then finally, we implemented a random number generator. One of the viewers found this simple one. Start with a seed equals some long constant. You add in another long constant every time you ask for a number. And the return result is whatever the current seed is, mod the base you want the answer in. Okay. So 150, we load that seed. It's already initialized to that 345 number. You load that into the X1 X1 register, and then the old seed. You take that seed value, and then we're going to build this constant that corresponds to 910 whatever, using that same trick of a 2 instruction load to get a long constant in there, a 32-bit constant. Then we do the arithmetic in 158. Seed equals seed plus 910 is that 158. Add W1. W1 gets W2. And we'll save that value into the seed variable, which is up there at, we first set X0 up in 150, so it's still there. And then we have X1 is the generated value. We push it on our data stack. We call our swap routine, which will push, we had the modulo on top of the stack, then we push the random number. We need it in the opposite order. So we call swap, and then modulo takes the random number modulo the base and calculates that and puts it back on the stack. So those last two routines are primaries in our 10th language, but we're using them here because it's convenient. All right, now, I don't think this is the fanciest random number generator, but we don't need particularly good random numbers for what we're doing, I don't think. We'll get fancier if we have to. We're going to make a game next week. So somebody suggested Hangman, so we'll do that. If you haven't played it, it's a word guessing game. So one person chooses a word and then writes a dash for every letter in the word at the top there. And then you draw a scaffold, and the other player starts making guesses, and they guess, like here we guessed N. Well, we replace all those dashes with N's where they are in the word. And then they guess C, and the person hanging there wasn't there. Then you draw the head. Then we guess A. Well, that's in the list. It's fine. And you add it. And then they guess X, and it's like, that's not in there. Okay, now you get a body. And your goal is to guess the word before the body gets filled in and the player is hung. Not a politically correct game, but it's about the right size for us. Simple test for us. We want to create something in this new programming language. We know we'll need a few primitives along the way. Probably we've created a bunch, but we haven't created everything you'd possibly need. So we may do a little alternating back into low level, but my hope is this will be a pretty high level thing. Just one simple game, maybe another thing, we'll see. But I want to prove out that the compiler stuff we've done is working. If it were a real project, we'd need to do file I/O. We haven't done that. We'd probably want to do better checking on stacks and things like that to make sure they don't overflow or underflow. And we'd probably introduce some debugging tools. Just the little bits of code I've already written, I've made multiple mistakes already, so I know I'd want some help there. We are going to do TDD on that, so we'll end up creating a small test framework in 10th, and then the application as we go. All right. Well, If you'd like to join us, where we meet Monday through Thursday, 2 to 4:30 p.m. Eastern Time or 6 to 8:30 p.m. UTC, you can catch us live at xp123.com/Twitch, or you can catch the older sessions at xp123.com/YouTube. They're the old sessions, 2 or 3 weeks old, lightly edited. I hope I get to see you sometime now, this week or in the future. Take care. Bye-bye.